These are the notes for the end of section 2.1 and the start of 2.2. Example 1 asks us to evaluate the limit as delta x goes to 0 of 3 times the quantity x plus delta x to the 8th minus 3x to the 8th all over delta x. So the way we did this previously was we would have to expand this, which to the 8th, we don't want to do that, and then cancel, factor out a delta x, cancel those. The way we want to do this now, last class we learned that the derivative of f of x is the same thing as the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. So looking at this, if f of x is 3x to the 8th, f of x is 3x to the 8th after the minus sign. Notice this would be f of x plus delta x, 3 times x plus delta x to the 8th. It would match up with what we're given here. So once we identify what f of x is, we can just take the derivative to evaluate that limit. Part B is similar. It has an h instead of a delta x. And notice there's no x here. But we're going to start out the same way. There's just going to be one more step we need to take a look at. Notice my f of x in this case is square root of 9, but it's square root of x at x equals 9. Recognize this as the limit definition of derivative. So to take the derivative of square root of x, we're thinking about x to the 1/2, 1/2 out front, subtract 1 from the exponent, and then plug in 9. This is equal to 1 over 6. Let's talk about derivatives of trig functions. The derivative of sine x is cosine x, and the derivative of cosine x is not sine x, it is negative sine x. Those are things you will need to memorize. There are other ones obviously as well, tangent, secant, cosecant, and stuff like that. We'll do those in a later lesson. Example 3 asks us to find the derivative of 5 sine x minus 3 cosine x minus 9x squared. So derivative of 5 sine x, derivative of sine x is cosine x, so it's going to be 5 cosine x. Negative 3 times negative sine x, so it's going to be plus 3 sine x. And derivative of minus 9x squared is minus 18x. And the fire alarm's going off. Sorry about that. Hopefully you didn't have your headphones in. That was probably loud. Example 4. I guess we skipped example 2, but that's okay. Problems like this, they're usually multiple choice questions, especially on the AP exam. Really, this question here is what we would be asked. The first time we do one, we're kind of going to think through these things in order to do this, answer this question. The really important points on your graph is that one, and that one. If you want to pause the video and sketch the graph for a minute, you can. Remember, derivative is the same thing as slope. So in part A, it's asking on what interval or intervals is the slope positive. So slope is positive starting now all the way at negative infinity until this x value right here, which is negative 1, 2, 3. So our slope is positive from negative infinity to negative 3. Now my slope is negative until negative 1. From negative 1 to infinity, my slope is positive as well. On what interval or intervals is slope negative? Slope would be negative right here from negative 3 to negative 1. And the slope is 0 at negative 3 and at negative 1. So if it's asking you to sketch a graph of g prime of x given the graph of g of x, I'd kind of think through these 3 questions. Usually it's not going to necessarily ask those questions. But to sketch the derivative, I'd start with where the derivative is negative. And I'm trying to graph derivative. I'm sorry, not negative, 0. And I'm trying to graph derivative. So my graph should be 0 at negative 3 and negative 1. So my graph is 0 right there on the x-axis at negative 3 and negative 1. I'm trying to graph derivative. From negative infinity until negative 3, the slope, which is my graph, should be positive. Not the slope of my graph, but the graph itself should be positive. So positive would be above the x-axis. And then my graph needs to be negative under the x-axis, and then it needs to be positive. As far as like how far down that goes, that's not important. Notice the graph that's given here is cubic, an x cubed. If I take the derivative of that, we do get a quadratic, which makes sense. It's a problem. Similar problem, you are given the graph of f of x. You are asked to sketch a possible graph of f prime of x. If you'd like to pause the video and try it, you can. If you're not sure how to do it, I'm going to explain it here in a minute. I would first start with where the derivative of the graph that's given is 0. So derivative is 0 at this point. So my graph needs to be 0. It's also 0 here and here. On this interval, from here until here, the slope of the given graph is negative. So the f prime of x graph needs to be negative under the x-axis. Whoops, that's terrible. That's not even a function. That looks better. And then the slope is positive. And then the slope is negative again under the x-axis, and then the slope is positive above the x-axis. Again, pretty bad drawing there, but you kind of get it. Should look something like that. A couple other things we need to talk about here. Next one is the difference between average rate of change and instantaneous rate of change. An average rate of change is the rate of change over an interval. It's the average slope. We can find that by taking the 2 endpoints and getting the slope. So we're just going to use, that's an algebra problem. That's y2 minus y1 over x2 minus x1. Because we have an interval, you have 2 points. So slope between 2 points, we're just using the slope formula. Instantaneous rate of change, now I want the rate of change at 1 point. Because I only have 1 point, now I need to use the derivative to find it. So example 6 here tells us the position of an object is defined as S of t equals negative 4.9 t squared plus 60t plus 1300. Part A wants to know how high above the ground is the object after 9 seconds. So how high above the ground, it wants a position. So we're just going to plug 9 into S of t. So we want to evaluate S of 9. This would be a calculator problem. and I get 1,443. They didn't give us any units here, but this is measured in meters. Part B wants to know the average velocity of the object over the first 9 seconds. This would be a good thing to know. Velocity is the rate of change of position. How quickly the object is changing its position. So when it asks for the average velocity, it wants the average rate of change. Velocity is rate of change. So what we're going to do is we're going to get 2 points, and we are going to find the slope. To find average rate of change, we found the slope. So I need 2 points. The first point, I'm looking at the first 9 seconds. So time starts at 0. That's going to be 1,300. The second point is S of 9, which we already found. And then find the slope between those. I get 15.9. If position's measured in meters, I've got meters on top, I've got seconds on the bottom. That would be meters per second. Part C asks, what is the instantaneous velocity after 9 seconds? So in part B, we're being asked, on average, how fast is it moving during those first 9 seconds? Part C, I want to know, at 9 seconds, how fast is it moving? Well, because I only have 1 point in time, I can't get 2 points and find the slope. So instead, we're going to use the derivative. We're going to take the derivative of that function. Velocity is the rate of change of position. It's the derivative of position. And then plug in 9. I get negative 28.2 meters per second. So that tells me at 9 seconds, for the most part, it's higher than it started. Its average speed is positive, but at 9 seconds, now it's moving down. That's why it's negative here. One last thing I want to take a look at here. If I have a positive velocity, that means the object is traveling in the positive direction. And a negative velocity pretty clearly means that the object is moving in the negative direction. So velocity will always tell you which way it's moving. So for that last example, we got the velocity at 9 seconds to be negative 28.2, I think it was. That means it was moving down. Negative in that case was down. It was moving up and then down. To tell if a particle or an object is speeding up or slowing down, we need not only its velocity, but its acceleration as well. And we do need both. So speeding up would be if velocity and acceleration have the same sign. So it's moving to the right, and then it's accelerating to the right. Positive velocity, positive acceleration, it's going to be speeding up. Or if it's moving left, if it's moving in the negative direction and accelerating in the negative direction, it would also be speeding up. And here, velocity and acceleration have opposite signs. One is positive and one is negative. That'll be it for today's notes. There's a couple other things we will take a look at together next week.